Good morning. My name is Edmund Chow, and it is my pleasure to introduce the first speaker of today's invited speakers session. Judy Chu is Associate Professor of Intelligent Systems Engineering at Indiana University. Her research is in data-intensive computing at the intersection of cloud and HPC technologies. Dr. Chu's research has been funded by the National Science Foundation, the National Institutes of Health, Microsoft, Google, Intel, and she leads the Intel Parallel Computing Center at Indiana University. Dr. Chu is the recipient of the NSF Career Award, the Indiana University Trustees Award for Teaching Excellence, and the Indiana University Outstanding Junior Faculty Award. Please help me welcome Dr. Chu.
It is really a great pleasure to be here, and thank Edmund for his introduction. I get to know him from the Intel Parallel Computing Center. We both have our own centers at a lot of common languages. Today, I want to talk about HubDAL as a new generation platform for high-performance machine learning. Before I get started, I want to first acknowledge our funding agencies. This project is not possible without getting the generous support from NSF. It's from the DIPS Big Data Solicitation and Program. And my program manager is there. Also, it's funded by Indiana University Precision Health Initiative. Of course, it's funded by Intel Parallel Computing Center grant. I have listed all my team, collaborators, and colleagues from Intel and NSF collaborators in the nationwide. So this work is really our team contribution. Given the interest of the public about big data, cloud, and HPC, our work is really work on the aspects of the convergence. So anybody think about the big data will think about the cloud, because a lot of data analysis tools are born in the cloud. On the other hand, a lot of audience in this conference will familiar with the HPC system, including supercomputers, exascale computing. So this is a totally separate community, have a different optimization, different algorithm, different applications. How to bring these two technique or software stack together is an intimidating task. What we want to do is find an approach to help with the convergence. And I will give you an example how we accomplish that by supporting machine learning on this convergence framework. In there, I will talk about the concept and how we do theoretical analysis to create computation models as approach and implement that as a runtime. The next part, I will give you some use cases. This is dear to my heart. We're building systems to support applications. We want to address emerging problems in the community. I will give two examples, including LDA and the graph problems. Finally, we conclude with our talk and discuss about prospective future works. What is HPC ABDS? So this is the concept behind big data and HPC convergence. A lot of people talk about this, but what does it really mean? How to do it? 4 years ago, we were funded by NSF to build middleware and high-performance data analytics libraries for data science. That is, the project has 6 partners, which is led by IU. One of the major challenging problems we observe is that data-intensive applications has to be supported by the community software. We have to evaluate, use benchmarks to have a systematic understanding what works well, what doesn't. This analytics has been extended support, not only data analysis, but also convergence of HPC simulation is the trending topic nowadays. One of the reports we based on for this observation is a NIST report. There we surveyed 50 applications and use cases, try to understand the user's requirements and what kind of software and computation needs. One of the nice things about this project is highly interdisciplinary. We have the following areas of applications, from biomolecular simulation, network science, epidemiology, computer vision, geoscience, remote sensing, and power science and pathology. This covers a broad spectrum of applications and data problems. One of the bold ideas developed is to create and implement cloud HPC interoperable software. What it means is that this software should have the performance like HPC, but on the other side, it should have the functionality like big data commodity systems, which is the most famous one is our Apache open source project. We have, over the years, published our ideas of this convergence and our architecture design with papers to big data and other conferences. Now, if we really want to develop and design the system, we have to understand not just the tools. Our survey suggests there are over 350 open source tools on the two development stack. So how do we start with this? We come back to the fundamentals, understanding of computation nature. So a lot of algorithms is taking the input and run the algorithm and generate the output. This is called sequential code. Many theoretical community is developing very efficient machine learning and data analysis algorithms. On the other hand, when you want to apply the algorithms to big data problems, then you have to scale it out. In this case, we do scaling using pleasantly parallel. Here we call it map only. Each of the mapper tasks do the same sequential code, but execute on different data set. So when Google becomes successful in processing large log data and indexing of the search engine, they developed a major tool is called MapReduce. This is a very simple pattern with parallel mappers followed by a reduction. And this is an amazing, successful tool, has been used and extended to support not only commercial, but academic big data problems. Now, when you look at the very right end, this is the HPC traditional system using MPI. A lot of linear algebra and scientific computation are based on this kind of a pattern of both point-to-point communication and collectives. So on one end, we have a high throughput big data problems. It's exemplified by MapReduce. On the other hand, we have a low latency, high performance simulation, utilize HPC technique like MPI. How to converge in between these two kind of a technique and software system. This becomes our idea of convergence, try to extend the applicability of MapReduce to support more classes of applications with high performance. Now let's talk about what is the ideas behind this convergence framework. MapReduce is very good in processing large type of data, but it's craftingly write to disk. So the shuffle phase is disk-based communication. With that observation, we understood if we want to support more complex algorithm, in particular iterative algorithm is very common in learning algorithm and graph algorithm, it doesn't work very well. The limitation of performance can be improved if we switch the disk-based communication with network-based, which we call collective communication. With that technique, we can improve the whole framework from MapReduce to map collective, which is implement the reduction using network communication collectives. We implement this whole framework and plug in as a library called HARP back to the Hadoop ecosystem. With that computation extension, now the MapReduce framework can support not only traditional big data problem, but also more sophisticated analysis and machine learning algorithms. This work has been done with 3 PhD research work over the last 15 years. In 2015, we established the Intel Parallel Computing Center at Indiana University. The idea there is Intel is trying to look at their newly implemented architecture and try to support data analysis. At that time, the first type of mining core machine called Xeon Phi has been released. We try to utilize the extensive computing powers of the cores to support analysis algorithm. They came up with the algorithm library called Data Analysis Accelerator library, built on top of their machine learning libraries. So in this library, they have 3 components. The first is batch processing mode. That means the library runs independently on a single node, like many core, multi-core machines. The second mode is distributed mode. So anybody interested in scale out to more than 1 node, they will utilize any communication or distributed framework to invoke the batch mode from Intel's library. And in the future, they will support streaming mode, which means that you can use the streaming analysis components. All of this data management API is supported on the very highly optimized math kernels like MKL, and utilized the TBB and other kind of optimization specific to the platforms. Now we actually have the technique. The lower level, we can utilize Intel's kernel libraries, highly optimized for their many core, multi-core platforms. At the high level, we can reuse existing distributed data analysis framework like Hadoop with extension to support iterative computation. We call it HARP communication. On top of that, we need to understand what is the challenges of doing big data machine learning. Is that just the input data or training data, or the parameter space of intermediate data? For that space, we're trying to analyze the computation models of different synchronization patterns we call HARP computation model. And this kind of theoretical understanding is very important to classify the types of machine learning algorithms. The end result of this theoretical research and software development is a library we call HARP collectives. If anybody look at the top 4 interfaces, it's very familiar, like an MPI type of communication. It has broadcast, reduce, or gather. The difference is all these collectives are optimized for big data problems, specifically for machine learning. At the lower level, we have 3 extra collectives, which is regroup, push and pull, and rotation. This is a data-centric communication pattern that do not exist in MPI. Regroup is commonly used by database operations such as join, and MapReduce is shuffle regroup. Push and pull is follow the parameter server, kind of a client and server point-to-point communication to accelerate model update. Rotation is the pattern, is highly powerful, is try to address big model problem that cannot fit into a memory, so they distribute the model and rotation through a ring or other topology. With all these techniques put together, the software system can achieve amazing performance. I listed 3 charts. The first one is k-means algorithms. We have 5 million data points of input data and has extremely large centroid data size with 10,000 centroid data points. And the features, a very high dimension, is 10. If you apply this to image analysis, commonly image features could be more than 10, could be hundreds to 500, even higher than that. So to address this high dimensionality problem, we utilize the computation model we mentioned and try to use the effective collective, such as origins, such as rotation, to address this problem. The result, you can see that a Hopdale solution can achieve a factor of 15 speed up over Spark's libraries. On the right-hand side is a subgraph counting problem. As we all know, graph problem is highly computation and communication intensive. Here, we choose a Twitter dataset of 44 million vertices and 2 billion edges. Subgraph template is quite large. It's 10 to 12 vertices. The common problem of subgraph counting, the simple case, is 3 vertices, is triangle. But when you increase the subtemplate size, it's exponential growth in both the computation and the memory utilization. The result shows that we can achieve, using Hopdale, a factor of 2 to 5 speed up over state-of-the-art MPI solutions. So this convergence is very impressive in the sense that for big data problem, the optimization and utilize big data tools. In the middle, we also compare with the GPU. So many people are interested to know, when you have a big data problem, do you use CPU-based solution or GPU-based solution? We find out that utilize the data set of 500,000 to 1 million data points, and with high dimensional features of over 300 running on single kernel machines, we can get a speed up of factor of 3 to 6 over GPU of K80 using the PyTorch software system. To summarize, we have created a framework, utilize HPC and big data techniques. And this is the Hopdale and has been created as an open source library. Currently, we already have implemented 12 algorithms of machine learning. It becomes an open source that available for the community in the GitHub website. Beyond that, we have another class of library members come from the community of our collaborators for different domains. It's customized algorithm. If you look at the list, they are clustering, classification, regression, structured learning, dimension reduction, and the graph. Very diverse problems. They can be applied to different science domains, and we summarize their features, including the vectors and different data types, including graph types. All of this has been applied using the technique we have using the collective communication to support highly effective the algorithms. Now let's talk about to the theoretical analysis of how to do machine learning and build the efficient library. We observe that currently a lot of machine learning libraries build upon individual implementation of algorithms with specific tools. It turns out that the real optimization problem or related issue has to be addressed ultimately at the solver level. That is because a lot of the classification of the task level of applications cannot capture the real trait of the computation. And many of the model structure for the iterative computation is dependable on the detailed choice of data structure, including vectors, matrices, tree, and other relevant data structure. In order to go to that route, we have to have a deeper understanding of a spectrum of machine learning algorithm, which we summarize here, of their features. Based on this understanding, we try to build a computation and communication pattern to fit into different category of machine learning algorithm. This abstraction is crucial for building a library. Very interestingly, we've observed the variety of big data tools utilize different patterns listed here. The first one is synchronized algorithm using latest model update. This basically is that each worker independently to update the model and synchronize sequentially. Of course, it guarantees the execution of the algorithm in correctness, but it sacrifices the performance because it's sequential. Common big data tools all utilize model C, which is called all reduce. So they basically concurrently update local model using workers, but followed by a reduction step to synchronize the global model data. And this is the most easy to implement as scaling, but it suffers from the performance. Model D is a very interesting one. It's called parameter server model. Here, the idea is each worker independently asynchronously updates the model. It scales very well because of the independence of computation and the model update. However, it's not guaranteed the algorithm can converge. The latest development is a model called model rotation, is model B. Here, it's trying to address the problem with the model size too big to fit into the memory size. In that case, one needs to partition the model and distribute them across the worker nodes. This is incredibly important to make big data high-dimensional problem feasible to implement at scale. Now, what is the approach when we have a new application of machine learning? People would commonly choose an algorithm or a favorite, and then go directly to find a tool to implement that. If you look at the top triangle, it's the common process. It works well for individual user, individual problem, but when you build a library, it doesn't scale very well because community of algorithm constantly improve and optimize, come up with a different algorithm. And different community are comfortable with different computing tools. Some are using big data tools, some are using MPI tools, some prefer Java over C++, vice versa. So there are a lot of dynamics in changing in the whole stack, what kind of tools, what kind of choices, what kind of algorithm. So this becomes a many-to-many problem. When you build a library, how can you build the kernel to support a variety of development in this space? So our idea is to abstract out the computation, which is suitable for different category of algorithm as computation models, which we explained in 4 directions, and then implement them with different programmable interface, which is the big data protocol equivalent to MPI for high-performance computing. We listed the 7 collectives. That is the programmable interface. When we identify that, we can implement all of this programmable interface with different languages. We can implement with Java, we can implement C++, and port to different kind of platforms from HPC to cloud. The runtime. When we have the computation model and we're given an algorithm, how do we choose the correct collective? Here we classify the different kind of choices. If we use the example as k-means, clustering algorithm, which is classify the input data points into clusters. For this very simple algorithm, we can choose, when the model size is very small, just broadcast to all the worker nodes to have a global synchronization. So common patterns and tools utilize broadcast followed by reduce. This can be further optimized by compress 2 communication with just one with all reduce. If the model size becomes bigger, the communication overhead will increase. In this sense, we can use different collective. We can use regroup all gather to combine intermediate data to make the communication more efficient, or we can use push and pull to do multicast kind of a communication. The major challenge is when the model size increase and cannot fit into the memory. And there are many cases for that. One we'll talk about later on for subgraph mining. Another one is recommender system, which you have huge matrices for a score calculation. In this case, we can use the rotation model to partition the model and rotate through different worker nodes. Why the collective communication is so important for big data processing? That is because the machine learning algorithm is very sensitive to convergence and consistency. High accuracy machine learning algorithm is the benchmark for the community to achieve. Think about deep learning to achieve the accuracy over 90 or 95% of image recognition. On the other hand, when you want to scale machine learning algorithm to large problems, there's overhead of system, including synchronization, communication, and computation cost. So there's order of magnitude of system optimization is needed for supporting big data machine learning algorithms. Our model is based on MapReduce to support collective communication. The computation pattern is bulk synchronous processing between nodes and within the nodes. So let me first explain why that existing big data tools has limitation for performance compared with HPC or MPI solutions. If you look at the communication pattern, for instance, all reduce or broadcast followed by reduce, the big data tools on the left-hand side will show you they have the iterations of broadcast and by a reduction. But on the other hand, MPI, do the optimization is in place interleave communication. It has long-running processing and threads. Unlike the big data tools, it's doing data transformation and has big overhead of creating new processes. Combined with the process overhead and communication optimization, that explains very well why these different kind of approaches give the performance differently. Now let's test if we use different approaches, what the performance result will become. We tested on 3 applications. One is utilize hop-down and k-means. Another is recommender system using different solvers. And if you look at the structure of this computation, they're very different. Some of them is very small model data with regular memory access. Others with huge model data with random memory access. And in some cases, the algorithm could be regular memory access, can be vectorized. When you look at the choices of the communication patterns, we separate into internode with all reduce and intranode with shared memory with vectorization using the kernels. And the performance result is staggering. You can see the chart on the right-hand side using hop-down and compared with Spark. It has a factor of 15 or 20 speed up or difference. Now, if we look at the recommender system and we utilize the internode rotation and intranode using asynchronous memory access and concurrency, this compared with the state-of-the-art MPI implementation is called a NOMAD, and we still gain a factor of 1 to 2 performance improvement. When you compared with a different solver using ALS, when you implement the intranode with all reduce, but the intranode with vectorization, you can see the drastic improvement of performance on the chart on the right. When you zoom in into the micro benchmarking to explain why you have the performance difference, here shows that the 3 different categories. On the left-hand side, the retiring means that the instruction numbers. And you also have the memory access with the L1, L2 bonded problem with memory and miscellaneous overhead. It becomes clear that a high performance computation and optimized algorithm can have less instructions, high accuracy, and more convergence speed. When we look at the profiling of the breakdown of performance, you can see clearly that at which level the thread will achieve the best performance. Since we use Intel's KNL machines, and we observed that 64 cores achieve the best performance in general. And different performance varies from whether you use vectorization or whether you can use the cache capacity for each computing node. Now let's look at a few use cases. LDA is a topic model. It's a very complex algorithm. It's irregular, dynamic, and it's difficult for load balancing. However, it can be applied for text mining problems where you have a bunch of data in a document with words, but the idea is that try to find out what is the hidden topics in there. So basically, you try to mine unknown features. That is a very powerful tool when working on applied to text mining. On the other hand, bioinformatics people doing gene sequence analysis, they cannot have the computation to support the entire protein sequence database search. However, they want to know the relevance of sequences in a quicker way. They can apply the LDA algorithm to summarize the topics of different categories. All of this boils down to modeling mathematically of decomposition of matrices, which you can see on the bottom right. So we wanted to find the topics and discover them by iteratively refine the model and update, which consists of a word document matrix, word topic matrix, and the topic document matrices. It turns out it's a multi-model synchronization for iterative computation. We do this by utilizing the rotation model, where each of the workers look at the steps when they load in the document word data, but generate intermediate models as indicated in the previous slides and rotate through them to do model update. The whole idea here is maximize the efficiency of parallel model updates, at the same time reduce the communication overhead. We can further implement the algorithm with optimization doing pipeline. Here, there are workers doing the computation at the same time and shift out the communication or data to the worker of the neighbors. So you create a very steep pipeline can further hide the communication overhead to accelerate the execution. Internally to the node, for shared memory, one can use concurrent threading to do asynchronous update. So combined with intranode communication optimization and internode thread level concurrency, we can achieve very high accuracy and convergence rate. This is compared with state-of-the-art parameter server solution, Phantom. You can see the model likelihood grows higher is better, faster is better for convergence. And the blue line is the HARP implementation. Red line is contrasting the Phantom implementation. And both charts shows that HARP outperforms the other solutions. We run the machine learning algorithm not only on the high-end HPC servers using Haswell and KNL, but they also compare with running on Big Red 2 supercomputer. And if you look at this two chart, it's very interesting observation is we run the same algorithm on the Cray machine, utilized 120 nodes, while the same task we can run on 30 nodes of high-end servers of Haswell and outperforms the other one. So that said, that high-end server, including many core KNL GPU, will give you huge capacity because of the parallelism. And for complex problem, that is much more efficient than commodity systems. The last application I want to show you is subgraph counting. Subgraph counting is a very challenging isomorphics problem, which is NP hard. The computation exponentially grow when you have the large data templates. And also, it's irregular communication with huge data volume. In this chart, we try to compare a subtemplate with tree-like structure, increasing the node from small template to as large as 12 and 15. We use the large data set from Twitter to compare with the different implementations of MPI. And we achieved a factor of 2 to 5 performance improvement. Why we can do this? So there's a community who implement the graph algorithm using MPI. There's another community in big data also use the tools, including Graph Lab. What are the differences? When you use MPI for communication, such as all-to-all, you basically spawn static processes and do communication based on the process between processes. What you identify is sender and receiver send the messages between them. For big data problem, the routing is very different. The data is the identification by partition. The routing is based on the data itself. What is the identification? Think about the MapReduce and key value pairs. Key is the regroup routing protocol and using hash function. This is very critical for data-intensive or big data problem because at the runtime, the data and distribution is dynamically changing over iterations. It works much better with user-defined function to dynamically define the routing protocols for big data computation. Here we show that we have flexible adaptive routing algorithms. The first stage is ring. The second stage is the neighbors. We can go through different kind of stages of communication that is optimized for the data distribution at the runtime. To sum it up, so we can use the routing of data-centric approach for communication for big data and dynamically update the routing protocols. And we can further couple that with pipeline to hide the communication overhead. Apply this kind of a strategy to one of the data set is the largest we can find in literature for open source, which consists of 65 million nodes, 5 billion edges, and the template size is 12 vectors. For this large subgraph counting problem, we utilize 25 nodes of Haswell multi-core machine. It took only 30 minutes. Conclusion. We try to study the correct approach to do big data and HPC convergence. We identify that a lot of existing community tools coming from the Apache big data software stack. On the other hand, HPC technologies is very helpful for the increased performance and productivity. So we find a solution for the HPC big data convergence and utilize HopDAO as an example to show that we can achieve the faster solution for machine learning or graph applications. This not only supports the community software and the ecosystem, such as Hadoop. We believe this approach can also be extended to support other big data tools or frameworks. We utilize Intel's data analysis kernel, which is a building block that highly optimized for their platform of Xeon and Xeon Phi architecture. This whole approach is much more sustainable. And we are very inspired by HPC community over the years build scientific applications and libraries such as MPI and PESI, all these kernels. We're hoping we can build these kernels for big data analysis. One of the theoretical studies is the identification of 4 computation models that set up the scene of different classes of machine learning applications and how to optimize their communication and computation. We implement HopDAO as a collective library with 7 collectives we've listed earlier. And right now, we already support 12 HopDAO algorithms of common machine learning applications. And in addition, we have a full range of 34 algorithms in the SPIDO big data project. I will want to make them open source for the community to use them. The next step is we want to start HPC Cloud Incubator project in the Apache big data community. So we want to benefit more users in this space. To conclude, we have 3 key technical components give HopDAO the world-leading performance. We extend from traditional big data using Hadoop ecosystem, utilize these techniques with Intel's analysis kernels to support a range of machine learning algorithms and applications. We can apply the core machine learning algorithms to very challenging image classification or image clustering algorithms. And to end up with my talk, we're currently prototyping to add a Python interface to invoke the highly optimized library and the framework. We know that scikit is a very popular Python code for machine learning. There are a lot of users use them. The limitation is that it doesn't scale very well. So our dream is that we want to transparently switch the engine to HopDAO so that we can allow users to program in Python environment, but run it into the cloud environment. We just gave a tutorial in Intel's conference of HPC developers that create the images on the Google Cloud and utilize very simple command lines to execute same machine learning algorithm as in the Python libraries. To end this up, I want to show you a simple demo. One just needs to log into Google Cloud and start a Docker container. There's 2 command lines. And we have a prepackaged images on Google Cloud. So now you can just execute a Python command line and run the image clustering algorithm using HopDAO. Now the whole software stack, as we described, can run successfully and generate the images, which will show you that we compare different clustering results and has very similar classification of different images. To end this talk, I want to show you a resource which we have put out as tutorial for a class of algorithm of machine learning, which is open source. And I have demonstrated bioinformatics, computer vision, graph, and text mining, all of this application can be effectively used, our algorithms and the framework. The nice thing about this whole approach is we provide a framework and collectives just program big data analysis like an MPI, but customized for data-intensive problem. One can also use simple Python interface to invoke existing library and algorithm to run it on the cloud or HPC system interoperably. So we want to take the next step and very excited to have the collective knowledge and intelligence from the community and want to work with you for the future applications and challenging problem. Thank you so much.
We have time for maybe one question. Is there anyone in the audience with a burning question?
Please.
Can you compare with TensorFlow? TensorFlow is also a framework for machine learning.
So the question is whether or not you can compare with TensorFlow.
Yes. We have students, graduate students, already worked on compare with TensorFlow. I only showed one result for PyTorch. So our next step is that we want to have an extensive comparison among other popular frameworks, including TensorFlow. We want to compare also with the different platforms, GPU versus KNL or many-core. We feel that it is incredibly important at this stage to have a thorough benchmark to find the result, what works well for different platforms and different kind of software tools.
Let's thank Dr. Chu again for her wonderful talk.
Thank you.